Okay, good day. We will have a topic today about structural irregularities, no? Sa ating earthquake engineering. So, first, let's define what is structural irregularities because this is very important na malaman natin ano ang mga structural irregularities sa mga buildings so that we can design it properly based on the National Structural Code of the Philippines or in the standard codes. Okay. So, first, structural irregularities, no? Irregular structures, no, masasabi natin sila na irregular structures if they have significant physical discontinuities in their configuration or in their lateral force resisting system. So this is defined under paragraph 1 of 28.4.5.2 of NSCP 2015. So according to the NSCP 2015, we have two types of irregularities, no, structural irregularities. Okay, so the first one is vertical irregularities. The second one is second category is horizontal irregularities. Under these vertical irregularities, we have stiffness irregularity, weight irregularity, vertical geometric irregularity, in-plane discontinuity irregularity, and weak story irregularity. And under the horizontal irregularities, we have torsional irregularity, reentrant corner irregularity, diaphragm discontinuity, out of plane offsets, and non-parallel systems irregularity. So first, let's discuss vertical irregularities. So I will discuss each of these types of irregularities starting from stiffness to weak story irregularity. So first, let's go with stiffness irregularity. As you can see here, no, this is an image where we can see that the displacement or the drift, no. So this is the drift. Okay, this is the drift, no, where the displacement and the drift is defined, no, according to mathematical modeling or in structural analysis. And this F, no, F is what we call the force or the strength of the structure per floor. Okay, so stiffness irregularity or soft story is based on its own stiffness from the word stiffness. So you can see stiffness is defined as something that the force, no, the force is directly proportional to the displacement or the drift, no. So that is K, no. So let's see what is stiffness irregularity or soft story as defined by NSCP 2015. So we can say that we have a soft story if the lateral stiffness of the lower floor is less than 70% of the story above it. So that is Ki, the story in question, is less than 70% of the story above, or Ki plus 1. Let's say we have a stiffness for the first floor. That means we will have a soft story if the stiffness of the first floor is less than 70% of the stiffness of the second floor. And we can also define that there is a soft story if there is if the first floor is less than 80% of the average of stiffness of second floor, third floor, and fourth floor, or the average of 3 stories above that floor in question. So according to table 208-9 NSCP 2015, this is what we call type 1 soft story. And in an ASCE 7-22, we have two types of soft story. So in NSCP 2015, we only have what we call the regular soft story. They do not account for the extreme soft story as defined in ASCE 7-22. So therefore, in a soft story, we have two types of soft story or stiffness irregularity, that is type 1A and type 1B. So for type 1A, we call it a regular soft story, and for type 1B, extreme soft story. So what is a regular soft story? So like I said earlier, regular soft story is that the floor in question, its stiffness, no, is less than 70% of the above floor or the floor above it. Or the first floor or the floor in question is less than 80% of the average of the 3 floors above it. So in extreme, we call it extreme soft story if the floor in question is less than 60% of the stiffness of the floor above it, or the stiffness of the floor in question is less than 70% of the average stories above it. So let's try an example here. No, let's try an example here. Okay, we have this Excel. Okay, so let's say we have building A. Building A has, I think, 10. No? 10 stories, beginning with the ground floor up to the roof deck. So suppose this ground floor and roof deck has stiffness, depending stiffness. No, they have stiffness for each floor, and for each floor they also have a lateral strength. So our unit for stiffness is kilonewton per centimeter. Okay, then our unit for the lateral strength is kilonewton. Therefore, our drift will become, the unit of our drift is centimeter, since we have an equation. No, we have an equation, so our equation is this. No, okay, so drift is equals to F over K, F over K. That is kilonewton over kilonewton per centimeter. Therefore, our unit for the drift is centimeter. Okay. So first, what is drift? First, we'll define drift. Drift is the relative displacement of another floor to the other floor. So drift, this is the drift of the first floor. That is, the displacement of the second floor minus the displacement of the first floor. That is the drift. So like I can say, we can try this one now. So as you can see here, we have this one. So the drift is the displacement at the first floor minus the the displacement at the floor in question minus the displacement at the lower floor. Then we can get the drift by dividing the lateral strength of its stiffness. And we can get the drift ratio by dividing the drift over its height, which is, I assume, let's say 3 meters or 300 centimeters for all story, and multiply it by 100%. Okay, so we can try doing this, no? So as you can see, we don't have any drift, no, stiffness, because roof deck is the final floor. So we can start here, no, is equals to this stiffness divided by this stiffness. So the stiffness of the 9th floor divided by the stiffness of the roof deck. So we will have a soft story if this value is less than 0.7, and we will have an extreme soft story if this value is less than 60% or 0.6. So we have 0.87. That means that this is greater than 70% of the ratio of floor number 9 to the roof deck. It means since it is greater than 0.7, we have we don't have no soft story for this floor. So let's try dragging this one and find out that what story is our soft story, if there is a soft story. So I will drag it down here. So as you can see here, unfortunately, our ground floor has a ratio of 0.68, and that is a regular soft story. So we have a regular soft story, which means our structure has an irregularity. So we can try this one. No? Let's start here with 7. Okay, we can start here. So 7, so story 7 divided by, so if you have less than 0.8 of the average above this floor 7, we can have a soft story average. Okay, so the average here 3, and enter. So we have that one. So this one, we can have this one divided by wisdom, or this one divided by average of these two. Okay, so this one I will drag. If there is less than 80%, then we have what we call a soft story, regular soft story. If it is less than 70%, we can call it extreme soft story. So as you can see here, we have this 0.78. So therefore, this 0.78 is less than 80% of the stories, of the 3 stories above it. That means ground floor, yes, is confirmed to have a soft story. Okay, so let's try. So what is this drift? So why do we need to find the drift? Because as you can see here, we have an exception. Okay, there is an exception. we can dismiss its the condition of soft story for that floor if there exists no story drift ratio greater than 1.3 times the drift ratio of story above it. So, according to NSC in ASCE 7-22, extreme soft story is not permitted. But we are not using ASCE 7-22. We are using NSCP 2015. So, what does this mean? Soft story does not exist if no story drift ratio is greater than 1.3 times drift ratio of story above. So, if the drift ratio divided by the drift ratio of the above story is less than 1.3, then there is soft story. If it's greater than 1.3, then we have no soft story. Okay, let's try doing this drift. So drift is equals to lateral strength divided by stiffness. So we can have this one, 3.58 centimeter, and dragging that one. So our drift ratio is just equal to this one divided by 300 centimeter. So we have 1.19%. So these are our drift ratio or DRs. Then we can try this one if we have if there is less than 1.3. Okay, if there is less than 1.3, then we have what we call a soft story. So this one divided by this one. Okay, so okay, so we have sorry, like I said, if there is greater than 1.3, then there will be soft story. Okay, as you can see here, there is greater than 1.3. Therefore, we cannot dismiss the soft story. Hindi natin pwedeng tanggalin ang soft story ng ground floor because yung drift ratio ng first floor divided by the drift ratio ng second floor is greater than 1.3. So, okay sana dito sa lahat, no? Para because they are less than 1.3, but unfortunately here may greater than 1.3. So therefore it is confirmed that ground floor has a soft story. So what can we do? So we can do is by increasing the lateral strength or increasing the stiffness. So it's the design here, the decision here is either we increase the lateral strength of the first floor and the stiffness of the first floor. So increasing its lateral strength is adding more reinforcement, adding more shear strength to this one, or making the dimension greater, no? Palakihin, increasing the dimension, I mean. So let's try doing this. So let's try putting this one into 2,900. Sorry. So by increasing the lateral strength, we also increase the ratio. So therefore, to prevent this one, we should increase the stiffness. So how can we increase the stiffness of the ground floor? We just need to increase the dimensions of the columns, or we can add another shear walls in the first floor, or we can add bracings just to increase the stiffness. So let's say we increase the stiffness to 1080, greater than, or we just need to equate it to second floor. So therefore, the soft story condition of this building A has been removed by just increasing the ground floor. From 736, we just increase it to the value equal to the stiffness of the second floor. Okay, anyway, let's go back to our vertical irregularity. So as you can see, extreme soft story is not permitted for seismic design category E or F. So I will not discuss this one because we are only focusing on NSCP 2015, in which extreme soft story are not considered yet in NSCP 2015. Until then, they should update this one. Okay, so the image source here is FEMA. So another irregularity is what we call the weight or mass irregularity. So this is just straightforward. That is a mass, no? There is a mass irregularity if any story has 150% effective mass on its adjacent story. So supposed to say we have like this one 150 tons, and the story above it is just 99, and the story below it is 98. So as you can see here, it is greater than 150%. So we have a weight or mass irregularity. So anything that is adjacent to it, that is its effective mass is greater than the adjacent floor. So that's a mass irregularity or weight irregularity. So according to table 28-9, this is what we call type 2. So type 1 is stiffness irregularity and type 2 is weight mass irregularity. So there's an exception, that is, irregularity does not exist. So same with the exception in stiffness irregularity, no? If there is no drift ratio greater than 1.3. Okay, so if there is no 1.3 drift ratio before in the lower floor over above floor, then we don't have mass irregularity. Same with the stiffness irregularity. So I will not elaborate more here. This is just simple. So vertical geometry irregularity. As you can see here in this image, we can see we have a vertical geometric irregularity if this DI, no, if this DI is or the DI below a DI or the length, no, or the length of the geometry of the building has, okay, we can say how the NSCP defined it. So as you can see here, if the horizontal dimension of the lateral force system, resisting system. So you can see here, we assume that the lateral force resisting system is a wall, shear wall, no? Assuming that the shear wall of this second floor or the second floor, this floor in question is less than, is 130% greater than, let's say, this one, or 130% lesser than this one. So anyway, we have vertical geometric irregularity if the dimension here, let's say the dimension here is 6 meters and the dimension here is just 3 meters. So as you can see here, if this horizontal dimension is 6 meters and this horizontal dimension is 3 meters, so 6 divided by 3, that is almost 200%. So we have what we call vertical geometric irregularity. So this is what we call type 3. So penthouse is just an additional floor put in the, mostly penthouse are put in the very most or topmost of the building, no? Like for example, this is a penthouse. So penthouse is not considered, no. Need not be considered if the penthouse is just one story. Unfortunately, this penthouse is 1, 2. So we have this, so first floor, second floor, and third floor. So if our penthouse is just only this one, so we cannot consider the vertical geometric irregularity of a penthouse. But unfortunately, in this picture, we have 1, 2, and 3 floors. So we need to consider that this structure has a vertical geometric irregularity, subject that the dimension of the penthouse, no, the dimension of horizontal dimension of the penthouse is greater than 130% to the dimension, or lower than the dimension, or lower than 130% of the dimension of the floor below the penthouse. So this image, we don't have any dimensions, but if there is 130%, no, 130% difference or increase or decrease of the horizontal dimension, then we can consider the vertical geometric irregularity. Thus, we have a geometrical irregularity for this building. Okay, so penthouse, no? I hope you understand penthouse. Okay, so this is the penthouse. So okay, in plane discontinuity irregularity, this is what we call type 4. So earlier, this is what we call type 3, no? Type 3. So this is type 3. So this is in plane discontinuity irregularity. So we can have in plane discontinuity if the dimension of the lateral resisting system is has, no, greater than the length of those elements, we can have offset. So as you can see here, we have an offset. So let's say we have an offset of 4 meters and the lateral resisting system is just 3 meters, no? Okay, 3 meters. So since we have 4 meters of the offset, that is 4 is greater than 3, then therefore we have an in-plane discontinuity irregularity of this structure. So how can we avoid it? We make sure that the offset is less than the dimension of, let's say, this shear wall. So we assume that this shear wall is the lateral force resisting system. So according to section 28.5, no, point 1, point 5, point 1, point 1 of NSCP 2015, if there exists a type 4 irregularity, a special load combination. So, we need to insert this special load combination if there is what we call type 4 irregularity. So, this is what we call. So, you can find this one in section 202 for the different load combination in NSCP 2015. So, EM is the maximum effect of horizontal and vertical force as provided in section 28.6 of NSCP. So, let's try here to 8.6.1. Okay, so this is the 28.6.1. Okay, so this is what we call the earthquake loads, no? So EM is the estimated maximum earthquake force that can be developed, no? So we can use it to design specific elements of the structure. So we can use this combination if this will control this one, no? The overstrength, the ductility or the overstrength that this is a factor that will account for the overstrength of the structure times the EH. So EH is the earthquake load due to the base shear. So this base shear, we can find it in 208.5.2-1. So design base shear is for static force procedure, but we can also find it in what we call dynamic force procedure. I will not discuss about dynamic force procedure here or nor the static force procedure. I have a video about that. So okay. Then okay, so we can find out seismic force amplification factor. So the omega O is what we call the seismic force amplification factor. Okay, then F1, we can consider 0.5 factor, and L is the live load, D is the dead load. Okay, anyway, let's proceed. So we can have in plane discontinuity again if this is 4 meters, example only, and this is just 3 meters. In short, we can have in plane discontinuity if the offset is greater than the horizontal dimension of the length, no, of, let's say, shear wall. Okay, so we can go finally to what we call the final type of vertical irregularity, that is the weak story irregularity. So what is the difference between the stiffness irregularity or the soft story versus the weak story irregularity? So soft story is about the stiffness of the structure, the K. Weak story is about the lateral strength or the shear strength of the lateral force resisting system in that floor in consideration. So we can say that a weak story is one in which there is 80% less of that story in question versus above. So the story strength is the total strength of all seismic resisting elements sharing the story for the direction under consideration. So let's say if we have this floor plan, so we have this, and let's say we have this, okay, let's change the color. Okay, so we have these different columns. So each of these columns has what we call shear strengths or the lateral strength. So let's say our earthquake is this one. This is the earthquake in consideration, this in this direction. Then so therefore our total story strength for this story, let's say this is story 2 or ground second floor, is just we just sum it all. So if this is 10, 10, 10, 10, 10, 10, 10, so we have a total of 70 kilonewton. So if this 70 kilonewton is 80% of the strength of the upper floor, then we can say we have a weak story. But in NSCP, we only have one type of weak story. We call this one type 5, no. But in so it is also called discontinuity incapacity. Okay. So in ASCE 7-22, they consider two types of weak story. That is type 5A, the regular weak story. That is the weak story is the lateral force or the lateral strength of the story below is less than 80% of the lateral strength of the story above. So extreme weak story is just 65%, less than 65%. We can say we have extreme weak story if this is 65%. So this is very important. In NSCP, in section 2, 8.4.9.1, we can never have an extreme weak story above 2 stories or 9 meters in height. So, if you are designing a structure and you found out that there is an extreme weak story, then, and that structure is above 2 stories or above 9 meters, we should redesign. We should redesign the architectural design such that we don't have a weak story. So, I'm sorry, we can also consider the architectural design. The thing that we need to design is the structural design, sorry. So we need to increase the strength of the lateral force resisting system. We need to increase the strength of or the dimension of the column, of the shear wall, etc. Or we can put bracing so such that the stiffness will increase and the diff ratio will decrease, no? So we have many design considerations to prevent extreme weak story. And as you can see here, there is also an exception. So we can consider still a weak story if that story in question can resist the seismic amplification factor times the what we call the lateral force, or the lateral force from uh, the analysis, no? So doing static force procedure or dynamic force procedure, we can know the design design load or the demand. So if the design demand times the seismic amplification factor can be resisted by the story in question or the weak story in question, then we can remove, no? We can still use that extreme weak story. So how is that possible? So we can say that the ground floor is 65% or 60% less than the lateral strength of the second floor. But the ground floor, yes, it's extreme weak story, but it can resist, no? It can resist the demand times the seismic amplification factor. So if we are what we call, let's see what is the seismic, seismic, different seismic amplification factor based on NSCP so that you can have an idea. Okay, the seismic amplification factor from the word amplification, that means it will increase the story. So, as you can see here, the only permitted building seismic force resisting system or SFRS is the special reinforced concrete moment frames, if we consider the moment frames, and the amplification factor is 2.8. So let's say the story in question, no, has a demand of 60 kilonewton, 600 kilonewton, no, for all of that floor. We just need to times it or amplify it by 2.8. And if the total strength of that weak story, of that extreme weak story is, let's say, 600 times 2.8, 612, 18. So, let's say 20,000, 2,000 kilonewton, then we can rule out these system limitations. So, we can rule out these system limitations, no? Okay, so that's it for the vertical irregularities. Now, let's continue this discussion for the horizontal irregularities. So, again, the only limitations here is the weak story, no, irregularity. Other irregularities we can still consider, like this one. So later we can understand, no, if there is an irregularity except this extreme irregularity, we can still consider it in our design, subject to, later I will show you after our discussion in horizontal irregularities. Thank you. Okay, let's try an example of weak story. So as you can see here, like for example, we have this one, no. For each floor, for simplicity, we assume that all columns, and let's say the columns is the what we call it the lateral force resisting system of the earth or the earthquake force resisting system is the column for this 10-story building. Let's say for simplicity, all the columns for each floor have the same strength. So we can see here, we have the strength per columns, and we can see here the number of columns for each floor. So let's see if there is what we call weak story irregularity. So again, what is weak story irregularity? That is the strength of the story below is less than 80% of the story above it. Okay, so let's go back to the Excel. So we can get the lateral strength by just multiplying the strength per columns times the number of columns, and just doing this one. So let's see if we have an extreme or we have a regular weak story. So let's try this one. Okay, divided by this one. So we have 0.97. So if there is a ratio that is less than 80%, then we can consider it as a regular story. But if there is a ratio that is less than 65%, then we can consider it a weak story. So let's do this. So as you can see, in the ground floor, we have 75 or 0.75, the ratio of its lateral strength divided by the lateral strength of floor 2. So you can see the result is 0.75. So therefore, this is greater than 0.65. We don't have an extreme weak story, but we have a regular story since 0.75 is less than 80%. So what can we do such that we can eliminate the weak story? So the best thing to do is not by increasing the number of columns, because this is designed by the architect already that the first floor shall only have 15 columns. So it's either we add some shear wall to increase its shear strength against, or we increase its lateral strength against the lateral force. But if shear wall is not permitted, then we need to just increase the strength per columns. So let's say from 135.93 kilonewton, we need to increase its strength. So increasing strength of a column is the most simple way is increasing its dimensions. No. So by increasing its dimensions or increasing the number of reinforcements inside that column, or etc. So let's try doing this one. So let's say we increase it to 140. We just add another 5 kilonewtons for all columns. Let's say 140.6. So it's still not enough. So what if we do it we increase it to 150? So by increasing the strength per column, strength kilonewton, no, per columns in the ground floor from 135.93 to 150, we have just eliminated the regular weak story. Therefore, our building or building A has no weak story. So thank you. We will continue this discussion for in another video of this irregularity. In the next video, we will consider the horizontal irregularity. Thank you.